All righty. Good afternoon, lads and ladies. Today, we're going to do a few things. I want to pick up more or less where we left off last time, talking about applications of implicit differentiation and the chain rule. Specifically today, though, we're going to be moving into our first, what some might call real application, where the problem is not purely mathematical in nature, at least not necessarily purely mathematical in nature. So we'll be addressing some real world problems today, and we'll be addressing, we'll be learning techniques that one can use to address real world problems in general. Namely, I'm talking about related rates. I also want to let you know that we are sort of getting close to exam 2. We're getting there, certainly by the calendar date. By calendar date, exam 2 should be next week. Now, we are right now moving into section 3.9 on related rates. So we will still be having to talk about linear approximation, some curve sketching, L'Hopital's rule stuff, and of course, min and max problems. But after we cover those things, and although it looks like a lot, it really is not, we will be ready for exam 2. So beware. Make sure you're staying on top of things and don't fall behind. All right. So let me go over to the dot cam here. My lighting situation is very dynamic this morning. Is this pen? Focus, you fuck. Focus! There we go. All right. I may change colors here because this doesn't seem to like me very much. Or at least the camera doesn't seem to like it. Oh no, that's doing better, okay. No, Caroline, so exam 2, we're not going to finish all of the exam 2 material this week. So by the calendar, yes, exam 2 would be next week, but I think probably it's going to be the week after, right? So we are here, which means we have all of this material before exam 2. Really this material, we got to get to applied optimization as well. So there's like 1, 2, 3, like 4 sections. Some of these things are in the same section. Like four sections in the textbook between now and the exam. So probably not next week, but early the following week, if I had to guess. As always, the thing we do is we cover the material at the pace we can cover it, kind of based on how you guys are doing and how class is moving. And then once we're done with that material, we'll have the test. So yeah, if I had to guess, it's not going to be next week, but maybe like Monday after. So like 2 weeks from last class, something like that would be my estimate. I will let you know once we get a little bit closer and once I can nail down the date for sure. So today we're talking about related rates. Which is section 3.9. The basic idea is that you'll have 2 objects, 2 quantities, which change, usually over time, but change relative to each other. We'll differentiate through the algebra relationship and then plug some stuff in. So I know that's very vague and I want to be nice and concrete. So the easiest example that I can think of that I believe most people will understand well without extra background is a circle. A circle's area, A, is related algebraically to its radius, R, according to the rule or relationship, area equals pi times the radius squared. I think we would all agree on this. If you don't remember it, here it is. If you've taken a class like college algebra recently, you may remember problems like, if the radius doubles, then the area goes up by a factor of 4. Or if the radius triples, the area goes up by a factor of 9, shit like that. What we're going to do in this class is get a lot more specific. So what I'd like to know is how, let's say, suppose a circle starts with radius 1 and begins to grow, say 1 inch, and begins to grow, adding 2 inches to the radius every second. The question I'd like to ask is, how fast is the area growing at the moment when the radius is 5 inches? Okay. So I hope the setup is clear. I'm starting with a circle, radius 1, and it starts to grow. The area definitely grows faster than the radius, right? If the radius doubles, the area goes up by a factor of 4. So as the radius grows, the area grows even faster. I would like to know if I'm adding 2 inches to the radius every second, how fast is the area growing at the moment when the radius is 5 inches? Okay. So what I do is I begin with my algebra relationship between the two quantities. A equals pi r squared. And I differentiate implicitly on both sides with respect to whatever the thing is that's changing. So I'm measuring how fast the area is changing over time and how fast the radius is changing over time, right? The radius is growing 2 inches every second. That means I want to differentiate through this relationship implicitly with respect to t, which stands for time. So the idea is that A is a function of time, t, and R is a function of time, t. So when I differentiate on both sides with respect to t, I'm differentiating implicitly. So I slap d dt on both sides. Pi is definitely a constant. Pi doesn't change over time. It's just always that number, 3.1415926, blah, blah, blah. But the area and the radius, those are definitely both changing because the circle is growing. On the left-hand side, d dt of A is just dA dt. And this is the rate of growth of the area over time. On the right-hand side, the pi is going to pop out, and I have to differentiate r squared implicitly with respect to time. So that's going to be 2r. If I was differentiating with respect to r, that would be all I get. But by the chain rule, or if you like, using the rules for implicit differentiation, I would slap on a dr dt, just like we slap on a y prime or slap on a dy dt. Here, the thing I'm differentiating is r, and I'm differentiating with respect to t, so I slap on a dr dt. Does everybody understand where this bottom relation comes from? I don't recommend writing r prime because it's not clear what you're differentiating with respect to. So this is the one benefit of the Leibniz notation. It's very explicit about what you're differentiating with respect to. So the statement dr dt says the derivative of r taken with respect to the variable t. It's nice and explicit. There is a special notation that physicists use for derivatives taken with respect to time, and I'll show you that, but let's not rush things. So it's not the prime notation. We will not be using the prime notation here. So enemies of the prime notation rejoice. But if you are a fan of the prime notation and you want something similar to that that can be used when taking time derivatives, I will show you a special notation for it. But for now, the Leibniz notation is most explicit. So are there any questions about where this comes from or any other thing? That's a good question, Andrew. Any other questions? So then at this stage, what we need to do is ask ourselves, what do I want? The question asked, how fast is the area growing? Right? In other words, I want dA dt. But I want to know how fast the area is growing at the moment when the radius is 5 inches. So I can plug in 5 for r, but the other thing, I need to ask, what do I know? My answer here should just be a number, right? At that moment, the area is growing at 5 inches per second squared, or whatever, 5 inches squared per second. But in order to get a number out, I not only need to know the value of r, I need to know the value of dr dt. What is dr dt? Careful, it's not 2t, it's just 2. r itself you could write as 2t if you wanted, but dr dt is just 2. And we need to get to a place where we can infer this sort of thing directly from the language. So since the radius is growing at 2 inches per second, and since dr dt is the rate of change of the radius with respect to time, we're growing, so r is increasing, so dr dt, the derivative of r, should be positive, and it's 2. That's how fast the radius is growing. Every second, we're adding 2 inches to the radius. That means the radius is growing at 2 inches per second. So I know that dr dt is 2 inches per second. And I know that the moment I'm interested in is the moment when r is equal to 5. So now I can plug those things into this relation and get out dA dt. So at the moment, when r equals 5, dA dt is equal to 2 pi times the radius, which is 5, times 2 inches per second. I should really say 5 inches per second. So altogether, I have 2 times 5 times 2, that's 20 pi. Inches times inches is inches squared per second. So there's some dimensional analysis going on here as well, right? We're working with units because we've got real world stuff. Does everybody get that like 5 inches times 2 inches is like 10 inches squared? In the same way that if you take a box that's like 5 inches by 2 inches, its area is 10 inches squared. Like inches squared is the unit for area. So this is it. This is the result. At that moment, the area is growing at 20 pi square inches per second. Units are important here, yeah. Now this is a math class, and I'm not going to try to beat you to death with the whole units thing, but units are important, and they're a great way to check your work. If the units don't line up, you know you made a mistake somewhere. So if you're calculating an area's rate of change and it comes out to like, you know, miles per hour, you know you fucked up somewhere. Yeah, as always in mathematics, it's nice to leave pi as pi. If we wanted a decimal for this, and there are going to be some homework problems where they ask you to get a decimal rounded to 2 decimal places or whatever, then you would go ahead and use your calculator and multiply by pi. But certainly when working by hand, definitely on the test, and in most math problems, constants like pi or the square root of 2, I'd prefer you to just leave them as pi or as the square root of 2, that sort of thing. Okay, so the big deal here is this procedure, right? Are we comfy with this procedure? First, you find the algebra relationship between the quantities in question. Then you differentiate on both sides with respect to whatever is called for, in this case, time, and it will usually be time. Then you take the relationship you get between these derivatives and you plug in the bits you know to try and solve for the bits you want. This is a nice, easy example. They're not always quite this easy, but I want to make sure we're comfy with the concepts before we let things get more challenging. Any concerns here? Anything we're worried about or feels weird? Okay. Well then, let's try something else. There's another sort of classic problem here. The ladder problem. So a ladder 10 feet long is resting against a wall. The base of the ladder is 2 feet out from the wall. All right, so here's my ladder. Here's my wall. This, of course, is 90 degrees. And the ladder is 10 feet long. The ladder begins to slide. The base begins to slide out at the rate, at the speed, 3 feet per second. How fast is the top of the ladder falling down when the base is 4 feet out? Okay. So is it clear there's like a dude up here at the top of this ladder? He's doing some work. And the bottom of the ladder starts to slide out like this. I don't know if you've ever been on top of a ladder when something like this happens, but it's fucking terrifying. Because what happens is your ass starts falling. All right, the front of the ladder is going to stay leaned up against that wall and the base just starts to slide away. So you start falling down. If the base of the ladder is sliding out at 3 feet per second, how fast are you at the top of that ladder falling down at the moment when the base of the ladder is 4 feet out? That's the question. So to answer this question, we need to invent some variables. And one of the big differences between this problem and the problem before, I gave you variables in the setup. Here you don't have any variables to begin with. So this is the height of the ladder, right? how far it is off the ground. Let's call that h. And the distance between the bottom of the ladder and the wall, let's call that x. In order to get started here, I need an algebra relationship between h and x.
Wouldn't x be 2? Since in the question it says the base of the ladder is 2 feet out from the wall.
At the very start, yes. But remember what happens here is that the base of the ladder starts sliding out. So x is not always 2. X begins at 2, but it's not always equal to 2. So we can't assume that that base is going to stay 2 feet from the back, from the wall, because the whole point of the problem is that the ladder starts slipping, right?
Oh, okay, got it.
We start sliding out like this. So it's true that the starting configuration looks like this. And we could figure out what h is in that moment if we wanted to using the Pythagorean identity, the Pythagorean theorem. But we know that the base of the ladder is going to start sliding out, so we need to give it a variable, right? Because it is changing over time. And I'm glad you asked that, because this is one of the common mistakes, is that when you're drawing your picture, you end up labeling something that does change over time as a constant. So it's a good question, and it's correct to say that the thing does start out in that situation, but because we know that the base slides, we need to give it a variable. Okay, so remember what I said a second ago, we need an algebra relationship that we can differentiate through to start looking at some rates of change, to start looking at some derivatives. So what algebra relationship exists between h and x? Do we see any?
Could we use slope, something with slope? And as the slope changes over time?
Well, so it's true that there are some like slope-ish relationships here, and certain variations on this problem require you to think of it that way, but I would say there's a more foundational relationship here that's easier to work with. You guys see the dark triangle? That's a right triangle, isn't it? So the sum of the squares of the legs is equal to the square of the hypotenuse. We know that h squared plus x squared is equal to 10 squared by Pythagoras. Yeah, very good, the Pythagorean theorem. Now 10 squared is 100. So we have h squared plus x squared equals 100. And this I can differentiate through. So now I apply ddt to both sides, because again, I'm asking how are things changing over time? So I apply the operator ddt to both sides. ddt of 100 is 0, because 100 definitely is a constant. But on the left-hand side, neither h nor x are constants. So both of these need to be differentiated implicitly with respect to time. If I take the derivative of h squared with respect to time, I get 2h times the derivative of h with respect to time, which is dh dt. Everybody comfy with that? Like differentiating the outer function, I get 2h, and then I multiply by the derivative of the inner function. The inner function here is just h. So the ddt derivative of h is dh dt. And the same thing for the x's, right? I'm not differentiating with respect to x, I'm differentiating with respect to t. So here I'll get plus 2x times dx dt. So this is now the step where I stop and I ask, what do I want and what do I know? So what do I want? What am I looking for?
dh over dt.
dh dt, right. I want to know how fast is the height changing? At the moment, when x is equal to 4. What do I know?
It's
X
falling
is
on
4.
3.
Yeah, so I know I'm interested in the moment when x is 4, and I've already recorded that here. What was the other thing? I heard one other thing.
That it's sliding 3 feet per second.
Good. So dx dt is 3, right? Because x, this distance here, look back at this picture, the distance between the wall and the base of the ladder is growing. So dx dt is positive, right? If this was coming in towards the wall, dx dt would be negative because this distance here would be shrinking. But since this distance is growing, dx dt is positive, and I know exactly how fast it's growing. I know that the base of the ladder is sliding out at 3 feet per second. So this guy tells me that dx dt is positive 3. And the question of positive or negative is important, right? If the base of the ladder was being pushed in, then dx dt would be negative 3, and that would change your answer, of course. All right, so I know what I want, and I know what I have in hand to work with. So now I'll plug all of those things in. And I get 2h dh dt plus 2 times 4 times dx dt is 3. All of this is equal to 0. There's something else that I need here, isn't there? I can't just solve this straight up.
And you solve for h because you
Yeah,
have
good.
4.
Good. This is another common theme. So once you get to this step, oftentimes you'll discover that there's something else that you need to solve for and plug in before you can find the desired derivative. So what is h in this moment? Well, let's redraw the picture. The moment I'm looking at is the moment when x is equal to 4. So in that moment when x is equal to 4, I need to solve for h. I know that h squared plus 4 squared is equal to 10 squared. So h squared is 100 minus 16, which is 84, right? So in that moment, h is equal to the square root of 84. 84 is not a perfect square. We could maybe clean it up. But for now, maybe I'll just leave it like that. Therefore, my relationship here, I can rewrite as 2 times the square root of 84 times dh dt plus 8 times 3, this is 24, equals 0. Oh, sorry, let's get this up here where you guys can see it. And now I can solve for dh dt. So dh dt, I subtract over the 24, and then I divide by this. Well, 24 divided by 2 is 12, so this is negative 12 over the square root of 84. And what should my units be here?
Feet squared per second.
Careful. Just feet per second. So remember, h is measuring feet. If you look at the relationship we had in the previous step and do the dimensional analysis there, this is 2x, which is measuring feet, times dx dt, which is measuring feet per second. So you would have here feet squared per second. And then when you divide by the 2h, you'll get feet squared per second divided by feet, which is just feet per second. Okay, so I'm going to put this back up here. Zoom out a little bit so you can see the whole thing. And then if you wanted to, yeah, you could simplify the square root of 84 a little bit. So that's 2 times 42, which is 4 times 21. So that's 2 square roots of 21. And then you can cancel another 2 if and you wanna, and get negative 6 over the square root of 21 feet per second. But I would be perfectly happy with this. So I'm much more concerned with the calculus here than anything else. Okay. So these are kind of 2 classic related rates problems. Any questions on how we set up either of these or what we did to solve either of these? Oh, it's hot. One second, I'm going to turn on my fan in here. I'm starting to sweat. Okay. So there are some sort of more purely mathematical related rates problems. And I like those a lot. They're a lot of fun. suppose I have a particle moving along the graph y equals 2 sine of x. And its horizontal speed is 5 units per second. So 2 sine x, we may remember, let me chop this up a little bit, we'll call this, let's call this pi, we'll extend out a little further, call this 2 pi, there's pi over 2. 3 pi over 2. All right, so I've got a little particle and he's chilling on this graph and he's moving along the graph and his horizontal speed is always 5 units per second. I'd like to know how fast is the particle's vertical position changing as it passes through the point pi comma 0. All right, so at one moment he's there, a little later he's here, a little later he's here, a little later he's over here. Right, this particle is moving along this graph and its horizontal speed is constant, always 5 units per second.
What does the question say? It says how fast is the particle's what?
Vertical position changing. Sorry, this doesn't want to focus. I'll change the pen. I think it's the color of pen that it's not liking. Yeah. How fast is the particle's vertical position changing as the particle passes through the point pi comma 0? Are we all clear on what the problem is asking for? Maybe not in terms of notation, but I mean just intuitively. Do we understand what we want? So early on, the particle's going up. If I were to look right here at this moment, I know that the particle's vertical position is going up. It's increasing, so I would expect that the thing I'm looking for, the rate of change, would be positive here. If I were to look at this moment, I would expect the rate of change I'm asking for to be negative because the vertical position is going down. I already have my algebra relation, y equals 2 sine x. So remember, at any moment, this point is x comma 2 sine x. Because I'm on the graph, y equals sine x. I want to know how that vertical component is changing at the moment when I pass through this point. So I begin with my y equals 2 sine x. And I differentiate implicitly on both sides with respect to time. On the left-hand side, d dt of y is dy dt. And on the right-hand side, d dt of 2 sine x is 2 cos x times dx dt. So then the question is, what do I want and what do I know? Who can help me out with the want? What is the quantity that I want here?
dy over dt.
Good, I want dy dt at the moment when x is equal to pi and y is equal to 0, because that's this point, this moment. Turns out I don't need the y equals 0 part, but the x equals pi part I will need. What do I know?
dx dt is 5.
Very good. The 5 is positive because I'm moving to the right, and that's the increasing direction for x. If I was moving to the left, at that same speed, dx dt would be negative 5. Is that clear? Okay, so now I just plug these things in. The cosine of pi times dx dt, which is 5. What's the cosine of pi?
-1.
Yeah, so this is 2 times -1 times 5, or -10. What are my units here? What is it that's changing? It's the y position. And here the y position is just described in terms of this arbitrary units, right? Like 1 unit to the left, 5 units to the right. So this is 10 units per second. All right. I'd like to do one more sort of purely mathematical problem. If there's time, I think there is, yeah. But first, any questions on this fellow?
Can you show on the graph how it's moving -10 units per second? Like, is
Yeah,
there a way to visually see it?
there is, yeah. Right here at this point, pi comma 0, is the particle, if I'm going left to right, is it going up or down?
Down.
It's definitely going down, right? Now, to get the actual number out, that just tells me that dy dt there should be negative. It's hard to see. It's not coming straight from a slope because the slope of this graph is the same, but how fast I'm going down depends on how fast I'm going over. Does that make sense?
Yeah, yeah.
So I can't geometrically explain why the answer here is 10, but I can geometrically explain why the answer is negative. The answer is negative because we're visibly going down here as I go left to right. But the fact that the value is 10 is coming from how fast I'm moving to the right. If I was moving very, very slowly left to right along that graph, then I would be going down here very slowly. If I'm moving very fast along the graph from left to right, I'll be going down here very fast.
Got it.
Cool. All right, one more pure math problem like this, and then we'll take a look at one of the problems from the homework maybe. All right. Same sort of business here. A particle is moving along the graph y equals x squared at a horizontal speed of 1 unit per second. How is the distance, let me say, how fast is the particle moving away from the origin as it passes through two comma 4? Question mark. So my picture here here's y equals x squared. Here's 1 comma 1. Here's 2 comma 4. I'm moving away from the origin, right? I'm moving left to right. Maybe I started somewhere over here. And I'm traveling along this graph. I want to know, as I pass through this point, how is this distance changing? All right. The distance from my point, my particle, to the origin. So the straight line distance from my particle to the origin, how is that distance changing as the particle moves away? Again, here I have to invent at least one variable. The position of the particle on the graph I can call x comma y. What don't I have a variable for here that I need a variable for?
The distance from the origin.
Yeah, the distance. So let's call that distance d. Everybody on board with that? So I want to know what is, oh, actually, let me not call that d, because then we're going to have d, dt. That's ugly. We'll call it L for length. Okay. So my particle is moving along the graph y equals x squared. That means at any given moment, its position is something, comma, that thing squared. Everybody get that? But since it's on the graph y equals x squared, if its x component is x, its y component is x squared, because y is x squared along that graph. What I want is dl dt when x is equal to 2. What do I know?
Do we know x is 2?
Yeah, I know that I'm going to be looking at the moment when x is equal to 2, but what rate of change do I know?
dx dt is 1.
Very good. dx dt is 1. Okay. What I don't have yet is an algebra relationship between x and L. So how do I find the relationship between x and L? You need your distance formula. Remember that the distance from the point x1, y1 to the point x2, y2 is d equals the square root, I'll use a capital D. Yeah, I don't want to confuse us. Capital D is the square root of x2 minus x1 squared plus y2 minus y1 squared. Does everybody remember this distance formula from algebra? It is a right triangle thing, yeah. Well, no, it's more subtle here. Remember, I'm not looking for L, I'm looking for the rate of change of L. So it's different from the ladder problem, because there the base of the ladder is sliding out along a flat line. Here, this point is moving along this curve. So while it's true that the distance formula is a consequence of some facts about right triangles, you can understand the distance formula as a hypotenuse of a right triangle. The problem overall here is quite different. So what I'm going to do is I'm now going to find a formula for L using this distance formula. So the distance L from the origin, which is 0, 0, to my point, which is x comma x squared, is L equals the square root of x minus 0 squared plus, that's x2 minus x1 squared, and then y2 minus y1 squared is x squared minus 0 squared. Which can be simplified or written more simply as the square root of x squared plus x to the 4. Is this the same thing as x plus x squared? The square root of x squared plus x to the 4?
Nope. Oh, yeah, you take out 1x1, yeah.
It's not. Square roots never, ever, ever distribute over addition or subtraction. This is a very common algebra mistake, but this shit don't work, I promise you. The square root of 1 plus 1 is the square root of 2. 2 is not the same as the square root of 2, right? Same reason this doesn't work. So square roots, even though the square root of x squared is x, and the square root of x to the 4 is x squared, you can't take the square root of the two things separately and then add those up. Square roots do not distribute over addition. So we can't do this, as nice as that would be. Is everybody comfy with that? You could, yeah, you could factor in x squared under the radical and then split up the square root over that multiplication. That is an option. But there's an even better way to approach this problem. And it's to take this relationship and square both sides. So you get L squared equals x squared plus x to the 4. Yeah, this is just a quick note. This is bad algebra. For example, the square root of 1 plus 1 is not equal to 1 plus 1. Right, this shit doesn't work. So instead, we'll square both sides and rewrite it like this. Now this I can differentiate through implicitly with respect to time, giving me 2L times dl dt equals 2x times dx dt plus 4x cubed times dx dt. And here's where I think about what I know and what I want. I want dl dt at the moment when x is equal to 2. So I can plug in 2 for x. And I know that dx dt is equal to 1. So I can plug in 1 for dx dt. But I still need L. At the moment when x is equal to 2. So I come back to this relationship and plug in 2 for x, solve for L. So when x is equal to 2, L is the square root of 2 squared, which is 4. I'll write it out. 2 squared plus 2 to the 4, which is the square root of 4 plus 2 to the 4 is 16, which is the square root of 20. And again, yeah, the square root of 20 is definitely not 2 plus 4, right? Which would be what you get if you took the square root separately. This is 4 times 5, so I can write that as 2 times the square root of 5 if I want. So now we plugging L equals 2 root 5, x equals 2, and dx dt equals 1, we get 2 times 2 root 5 times dl dt, which is the thing I want, equals 2 times 2 times 1 plus 4 times 2 cubed times 1. So this is 4 square roots of 5 times dl dt equals 4 plus 2 cubed is 8. 8 times 4 is 32. So 4 root 5 dl dt is equal to 36, which means dl dt at that moment is 36 divided by 4 root 5. Which is just 9 over the square root of 5. And again here, this is units per second. Light. Yeah, there we go. All right. So these are related rates problems. Some of them purely mathematical in nature, some of them real world in nature. The homework problems have a mixture of both, although I try to keep things fairly tame, and I know that the real world situations you have more intuition about, so they're a little bit easier to notice when you've made a mistake. It's important that you put a lot of love into this homework because these problems are somewhat demanding. So I want to take a quick look at what we have up here and see if there's anything to warn about. First, any questions or comments on this last example? Everybody else feeling okay? It's not too bad as long as you follow that recipe, right? As long as you be mindful of the sort of procedure. Oftentimes you'll need to come up with a variable, right? So you draw your picture, come up with the variables that you need to label, discover the algebra relationship, differentiate through that algebra relationship with respect to whatever the appropriate variable is, write down the thing you want and the things you know, plug in the things you know, see if you can get the thing you want. You may have to go back and solve for something else. And then eventually, once you've found everything that you need, you can plug them all in at once and solve for the thing you want. All right, let me remind myself if I put anything rough in your homework this week. I don't think there's anything too scary here. Plenty of logarithmic differentiation. Oh, did I not add any related rates to this stuff yet? Oh, okay, that's why this is so short. Okay, I still have to add your related rates problem. So I'll go ahead and add those in right now. So I didn't put any of those in yet, but yeah, that's related rates, and I'll slap in some related rates problems to this current homework. So finish up the logarithmic differentiation stuff and then get started on the related rate stuff. Like I said, I won't put anything too brutal in there, certainly nothing harder than what we did here today. But if you do get stuck on any of it, feel free to bring it by office hours or shoot me an email, all right? Oh, I promised you a special notation for time derivatives. So if you don't like writing d whatever dt, there is a special notation for it. Instead of writing dx dt, you can just write x dot, and the dot goes over the middle. Or dy dt. If you don't like writing that, you can write y dot. For example, in that last problem, instead of writing dl dt, I could have written L dot. This is a pretty standard and globally acknowledged notation for derivative taken with respect to time. So a dot physicists use this. This is common in physics and engineering. Other places you'll see this is like, you know, that the velocity function is the derivative of position. So s is usually position. So s dot is v. V dot is a. And so you also know that v dot is the second derivative of position. So you could also say s with two dots like this for the second derivative is a. All right. But yeah, that's it. So if you don't want to write dy dt, dl dt, dx dt, whatever it is, then the alternate notation for derivative taken with respect to time is to just put a dot right over the top of the middle of the variable. And higher derivatives go like this. I don't think I've ever seen like third and fourth derivatives in the dot notation. I'm not sure if like in place of y triple prime, you would write like y dot 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 or y dot dot dot. But yeah, the dot notation works. If you want to use that, feel free. I'll know what you're talking about, and so will anybody else. Okay, that's where I'm going to end it for today. Like I said, wrap up the logarithmic differentiation problems in the homework, and certainly by the time you are done with that, I will have added the related rates problems. If you get stuck on anything or you want to talk about anything else, just come see me in office hours. Otherwise, I will see you guys on Friday, okay? All right, have a good afternoon, guys. Oh yes, question? Of course, of course. All right, take care.